intermediate value theorem and its uses in inequality. If you read the textbook, there's something called intermediate value theorem, and the explanation is very complicated. And because we don't need the full intermediate value theorem in this class, I'll just give you some simplified version of the intermediate value theorem. So my simplified version, intermediate value theorem, is often written as IVT. So IVT is the following. If a continuous function f of x has different signs at fa and fb, there must be a c between a and b such that f of c is equal to 0. Now, this may be already simpler than what's in the textbook, but I still owe you some explanation of what this means. Well, let's say you have a function which is continuous, and here's a and here's b, and they have differing signs at these two values. So let's say f of a is positive, f of b is negative, right? So this is f of a, that's f of b. If one's positive, one's negative, then what's going to happen in between? Well, the graph must be passing through these 2 points, right? So there must be a point C, I don't know where it is, but it has to happen between A and B, that f of c is 0, because when you have a function value equal to 0, it means that it's right on the x-axis, right? Any point on the x-axis has y value 0, so the function value would be 0. Okay, so when you see this, you should really think of this as meaning on the x-axis. Okay, so graphically, the above theorem is simply saying, oh, if you have something positive, something negative, and it's continuous, meaning the graph is connected, then it must pass through the x-axis. Okay, it must cross the x-axis at some point. Now, this is a very obvious theorem, and there is a rigorous mathematical proof for this IVT, but we'll just make use of it, okay? But before I show you when to use it, let me first explain to you that this continuous is crucial, okay? So I want to say continuity is a must, because without continuity we might have f of a here, f of b here, but then you can have a jump discontinuity, and the point might just jump from here to there, and now you've satisfied that f of a is positive, f of b is negative, so they are different, but there is no point where the graph crosses the x-axis. So that's why this continuity is really important. And then to give you some example of when we need it, well, you actually use it without knowing. So one example is when you have a TI-84 calculator to find zeros of a polynomial. So I bet you've done something like this when you were in Algebra 2 or pre-calculus. You're given like x squared minus 5x minus 7, and you can't find the zero of it. So what you do is you punch this into your calculator, and when you have a graph, then you say, oh, at this point it's positive, at the other point it's negative. And then if you give the calculator the left bound and the right bound, it checks whether the signs are different. Once the signs are different, then it just figures out where this point is by doing something called bisection method. Bisection method is it just goes to the midpoint, and if it's already positive, then it takes the positive part and the negative part and searches for the zero in between. If it's negative, you do the opposite. So there's this algorithm for finding the point C if the two signs are different. So this intermediate value theorem is already being used in Algebra 2 or even before without you realizing that you're using it. Now the second place where you'll be using intermediate value theorem is in inequalities. And this is again something that you've been using without realizing that you're using it. So let me show you how it's done. So let me write down an inequality question, say x squared minus 4x minus 5 greater than 0. Now how do you solve this? Well, step 1, you have to know that inequalities are much harder than solving equalities. So before you tackle the inequality, you first want to solve the equality. That's step 1. You solve set equal to 0, and you get x minus 5, x plus 1. So you see that x is equal to 5 and x is equal to negative 1. So you find the zeros. Now step 2, what you do is you put it on the number line. So here's negative 1, here's 5, and this is the entire number line. So negative 1, 0, 1, 2, 3, 4, and then 5, and so on and so on. Now you can see that the number line is now divided into 3 parts by these two numbers. And what you do in step 2 is once you put those numbers and divide the number line into many parts, you're going to pick sample values, test points. So let me give you an analogy. You know, in water treatment facility, to have clean water, they periodically sample the water, right? So if this is like a water treatment facility and you have like 3 pools of water or 3 tanks of water, and you want to make sure these are free from contaminants, what would you do? You would pick a small sample, and then you would measure them test them for contaminants, right? And that's exactly what we're going to do. We're going to pick numbers, one number that belongs in here, one number that belongs here, and one number that belongs here, and then test it to figure out if it's positive or negative. All right, now you're free to choose any number, but I like to choose multiples of 10 because that's easier to calculate. So I'm going to choose negative 10 here as the sample point from here. And I also like 0. 0 is between negative 1 and 5, so I'm going to pick 0. And then after 5, I'm going to pick 10. Now with these sample points, what you do is now, step 3, you evaluate. So we're going to call this function as f of x, and we're going to evaluate the function at each of these test points. So f of negative 10, well, that's negative 10 squared. Negative doesn't do anything when you square it, it becomes positive. 10 squared is, of course, that's 100, right? And then negative 10 times negative 4, that's positive 40, and then minus 5. So, well, that's 135. Well, the values are not important. You only need to know if it's positive or negative, okay? So we have determined that the function is positive here. How about f of 0? Well, that's easy. 0, 0, so you're left with negative 5, so that's negative. How about f of 10? That's the last test points. Last of the test points. 10 squared is 100. Minus 4 times 10, that's 40. Minus 5. So, well, it's positive, right? 100 minus 40 is 60, so it's positive. So it's negative here and then positive here. And then once you figure out the values of the test points, then you can now write the answer down. So the answer is Answer is x has to belong here and x has to belong here. So there are two intervals where this inequality is true. That's the interval from negative infinity until negative 1. Union the interval from 5 to infinity. Okay. A lot of times you're told to write the answer in terms of x. Now this is a case where all the numbers that belong here is less than negative 1. So this means x is less than negative 1. Or a number should be here or there in order to satisfy this inequality, right? So if you have a number that's in here, those numbers are bigger than 5. So that's another way to write down the answer. So either you write the answer in an interval notation like this, or you should write the answer in this way. Okay, so that's it. Now, the curious thing is, I've never said anything about intermediate value theorem when I solve this, right? So where is the intermediate theorem hiding at? Well, although you were never told that you're using the intermediate value theorem, it's actually what's behind all this. So there's this workhorse that's really working hard behind the scenes and you didn't know it. So where is it working at? It's the case how it's the way you justify how the sample point value determines the sign of the entire thing. So let's think about the following. Maybe somebody comes in and says, well, you told me that negative 10 gives you positive, but how do you know whether negative 5 would be positive or negative? Is there a reason for that? Okay. Well, then you can use the intermediate value theorem to argue something like this. If it's positive at negative 10, it's negative at negative 5, then by the intermediate value theorem, we know that polynomials are continuous, right? So it's going to have to connect these, so it has to cross the x-axis at some point. But if it crosses the x-axis at some point, what does that mean? That means there's a root of this, there's a 0 of this polynomial before negative 1, but already in step 1, we established that negative 1 and 5 are the only points where the function becomes 0. So there will be a contradiction. Therefore, because of the intermediate value theorem, the function has to stay positive until it hits negative 1. Now after negative 1, it's okay to fall down to negative because then if it's negative here and positive there, then of course this c value will be negative 1. It can go through the 0, so it's okay to be negative here. And you can argue in the same way that once negative, it has to stay negative until it hits 0. So that's it. That's where the IVT, the intermediate value theorem, really is working. Intermediate value theorem justifies that once positive, it has to be positive until you hit the 0.